In a precast plant, they've cut labor, probably 80% in the last 6 years. They don't have to vibrate the beams, and they get much better finishes on their concrete. But that's just one area of what would be a characteristic for a performance. Early age strength, if we wanted to fast track, if we wanted to rebuild an intersection, we wanted to get on it and off of it in 4 hours' time, you can do that. There's concretes that you can tweak that characteristic and make it happen. The idea here is to make engineers think, when we talk about performance, to have them begin to think that there's more that you can do to concrete besides just achieve strength. Strength is just where everybody's head has been for the last 100 years or so. If a little bit is good, a lot has to be better. But there's other things that make concrete fail, not just strength. In this case, we're looking at a stilling basin of a dam that we'll show a little video on here, that the concrete obviously was eroded away by abrasion erosion. That needs a concrete that has extra toughness. That's a performance that you need that can be improved. If you're making containment vessels for low-level radioactive, this is Hanford Nuclear Site in Richland, Washington. 12-foot thick slab or walls of concrete here. They're worried about heat of hydration. When concrete gets hard, changing from its wet state to a hard state, it generates heat as part of the chemical reaction. And in that big mass of concrete, in big thick walls like that, concrete can get pretty hot. If you have a core differential temperature from inside that slab to the outside of the slab that's greater than 36 degrees F, it'll crack. Well, obviously they don't want this to crack because it's supposed to last a couple hundred years and containing radioactive material. So they want it to be very volume stable and low heat of hydration. They don't want to generate a lot of heat. They want the concrete still to get hard and last for a couple hundred years, but they don't want it to hit 160 degrees when the outside environment's 50. So there's things that they can do to the concrete to make that work. It's not just driveway concrete, or to make longer life. That's where the FHWA spends most of their focus on how we get our bridges, as we heard in the video, to last longer. The last inventory in 2005 said we had just short of 600,000 bridges in the United States. These aren't culverts. I'm trying to think of the definition. They had a certain length that would actually make it a bridge. It's not just the culverts over the little creeks. It's a physical bridge. Of those 595,000, there's about 28% that are rated deficient. Deficient either because they're under capacity, structurally deficient, falling down. This bridge right here is in that category. There's a lot of Erie bridges like that in Pennsylvania, not just at Erie. But in Illinois, we're down to 18%. The national average, remember, is 28%. So Illinois has done a great job in the last 10 years of cutting that number down, because the original number, this thing was up around 240,000 10 years ago. A lot of states have done a good job at knocking the number down, and Illinois is one of them. Illinois has been using high-performance concrete. The first overlay was placed here in 1986. State Route 4 crossing I-55 is the overlay. It's still in place. They only expected the overlay to last 10 years, and we're up to, what, since 86? 20 years. So they doubled the life out of that overlay. An overlay was put on the bridge because the bridge was rated as deficient. Most of the bridges fail because of chloride attack through the surface of the bridge, getting into concrete, which acts like a sponge, sucks up the water, sucks up the chlorides. Once you get enough chlorides into the concrete at the layer where the steel is, that's corrosion is actually an electrochemical reaction that you need an electrolyte to carry the current through the concrete. And it's the chlorides, the negatively charged chlorides in the concrete that act as that current. A little bit beyond ourselves here. But the idea of an overlay is to repair, to get extra life out of a bridge that they would normally have tore down to put up a new one. So in Illinois' case, they got twice the life out of it instead of having to tear it down and start over again. We see a lot on parking garages, not just bridge decks. Parking garages are probably even more frightening because most of their decks are very, very thin. Most of their decks have post-tensioning cable in it. You see cables are all under tension and they're jackhammering out concrete because of corrosion and failure. This happens to be underneath the Amoco building in Chicago. which it's one of the 3 tallest buildings in Chicago. It's like 105 stories, and we're 6 stories underground jackhammering out the foundation. What's wrong with this picture? You know, we're taking out the foundation of a 105-story building above us. So this was made with conventional concrete. The chlorides were brought in by cars driving on the highways. They park underground in a warm building. The moisture and everything falls off the vehicles. They're underneath the building. There's no way for them to come out. They're there forever. They get into the concrete. Whatever gets deposited there stays there. So parking garages under buildings are notorious for this type of problem just because they're trapped. Whatever gets in there doesn't get out. Outside parking garages, yeah.
Did you say that it goes 6 stories underground?
Yes. I think it's actually like 8 or 10. No. That's cool. But what does service life mean on something like a parking deck or a bridge? This is a famous way of depicting it from Professor Tootie back in '82. Concrete acts as a sponge. That's this initiation period here, where it's allowing chlorides and carbonation to actually penetrate and get into the concrete. There's no corrosion happening at that point in time. It takes a certain amount of electrolyte in the concrete to start corrosion. That's where we see the corrosion starts here, and then as it corrodes, when steel corrodes, it effervesces and swells. It swells to 4 times its normal size. And although concrete's real strong under compression, it's real weak under tension. And the expansion of rusting steel is a lot of force when it swells up to 4 times its size. That causes the concrete to break. Once the concrete breaks, more water gets in, more corrosion, freeze thaw. You get potholes happen very quickly. That's the propagation period. The one bridge that had the sign of Erie pointing to it obviously was in this part of the structure, or was in this part of the equation of its service life, way beyond the initiation phase. But when do you pull the plug on a bridge? When do you say it's done? Well, that one's done. That happened a month ago, about 20 miles from my house, crossing Interstate 70. Luckily, no one was hurt. Imagine that no one was hurt on this. The bridge is 40 years old. The reinforcement was completely rusted through. It's on the shoulder, you know, so all the salts and all the waters and everything are going to run to the side of the edge of the bridge where the gutters are. That's where all the salts and everything got in. They lost all the steel there. There was no traffic on this at all. It fell down under its own weight. This building is rated deficient. It was scheduled to be repaired. Well, it is now. But there's 2 other bridges that were made all at the same time on either side of this one. PennDOT has since shut down both of those. And I think last week they actually blew up this one. So, I mean, you know, some states learn by, you know, taking it out of service before this happens. Sometimes the end of service life can be pretty dramatic.
This was a rough radio kind of thing?
Without the steel in the concrete is very brittle. It'll break like a pencil. That's why you have reinforcing steel in concrete. Steel's real good in tension. Concrete's real bad in tension. So if you put those 2 together, you got the good, you know, you got them both working together. But obviously the steel in this case was completely corroded through, so that it was acting like a pencil. The weight, just the weight of the bridge itself, the concrete couldn't carry it without the steel.
So overnight happened just in
Yeah. Yeah, it was like 5 in the morning when it went down. This happens in parking garages all the time. Bridges are more catastrophic because of their potential, but Minneapolis is famous for having parking garages fall down for the exact same reason, that the salts just corrode through the reinforcing steel and there's nothing left holding up the structure other than a concrete pretzel, and the pretzel snaps.
That was in Pennsylvania, you said?
Yeah, Interstate 70, just south of Pittsburgh. How do we make high-performance concrete? Well, concrete, real simple, is 2 ingredients. It's glue and it's the aggregate. The aggregate is your sand and your rock. Normally that's something that happens locally, that you're going to get out of the ground locally, and normally it's the best material that you have in your concrete. If you think real pragmatically about what happens with concrete, people complain about it cracks. It has carbonation, it has conductance, it takes in chlorides, it scales, it has creep, it has delayed etrignite. All these bad things happen to the mortar, except for alkali-silica reaction, which could happen from your aggregate, but that's something we know how to take care of. That's normally the aggregates are the best things you have. So You know, you're dealing with mortar here and you're dealing with aggregate. Those are the two things you're going to put in concrete. These cause you a lot of problems if you don't do it right. This is the good stuff in the concrete. So real pragmatically, I want to use more aggregate and I want to use the least amount of cement that I have. I want to make it the best glue that I can possibly make it, but I don't want to use a lot of it because a lot of it gets me into trouble. That statement alone that I just made to you is almost 180 degrees different than what everybody thought in the last 50 years in the concrete industry. You got a problem with your concrete, put more cement in it. No. If you add water to these three things, slag, Portland cement, Class C fly ash, they hydrate. What that means is they react. Chemically, they react with the water and become something different. Like baking a cake, you put flour and milk together and sugar and you bake it, it becomes something different. Well, likewise, when you put cement with water together, the cement starts reacting with the water and it starts growing crystals and the crystals interlac and that's what makes the strength. Slag does the same thing, Class C fly ash does the same thing also. They hydrate. Silica fume, or I wish I had a Class F fly ash picture here, but I don't. If you add those two things to water, all you made is dirty water. They don't hydrate. But if you remember that video, the fellow in New York was talking about this Roman technology where they used ash from Vesuvius. And what they actually did is they ground it up with a local limestone from Pozzolana, Italy. And when they put those two things together, this silica, which is in F-ash and silica fume, reacts with lime and actually makes concrete. It actually gets hard. It gets hard pretty good too, if you think of the Appian Way and the Colosseum and all these other buildings that are still up there. So we've got a technology here, this pozzolana chemistry, and that's really what it's called. It's called pozzolanic chemistry now. This idea of lime reacting with silica, amorphous silica, that's been around for a couple thousand years. Portland cement was patented in 1824, less than 200 years ago. So we only have 200 years of history of working with cement, this type of cement. It's called Portland cement because the color resembled the rocks that they found on the Isle of Portland, which is an island off of England. There's nothing to do with Maine or Oregon, or has to do with that island. But if we put these materials together, we can have some good things happen. If we combine this Portland cement chemistry with this pozzolanic chemistry, we can make a really good glue for our concretes. Even though all those materials look like powders, there's some difference in those materials. Slag, fly ash, two different types of cement, they all basically have the same particle size distribution. If you look at the D50, 50% of the particles, the D50 is probably about what, 12 micron, 13 micron, somewhere out there, 10 to 12 micron. The D50 of silica fume ends up being about 0.1 micron. Very, very fine material.